In this section, we're going to investigate methods of solving more complicated systems of equations. Right now, we're going to look at this system of three equations involving three unknowns. Our method of solution is going to be a little bit different. It's going to depend a lot on our ability to organize information and think rather carefully and so forth. But I want to make several comments here before we start. One is that as we progress through this course, we're going to investigate other methods for solving systems kind of like this. So this is not the only way we're going to solve systems of three equations and three unknowns. So we're on a road here. We're on a pathway of information. And this is just another stepping stone on that pathway. We'll have more efficient ways to deal with this situation as we progress. But the information we learn here will be useful for those purposes. Also, I want to mention that there is a graphical interpretation to this situation. If we have an equation that involves three equations, an equation that involves three variables, then the graphical interpretation on a three-dimensional coordinate plane, one where we have an x-axis, a y-axis, and a z-axis, which is perpendicular to the x and y-axis plane, you see, then we have a graph which turns out to be a plane. That is, the graph of this equation is a plane. The graph of this is a plane. The graph of this is a plane. So what we really have graphically is the intersection of three planes. Now to understand how that can possibly happen to where we'll have an intersection point, you see, of the three planes, just imagine the plane consisting of, let's say the floor and two walls in a room. Then you have the intersection of those three planes at a corner. You see, so that's kind of the idea. And we're looking for the coordinates of that corner, basically, in this situation. Okay, here's what we want to do. We want to take that system, this system of three equations and three unknowns, and we're going to go through a manipulative process. And we're going to change it into another form of three equations, a form where we can back substitute easily. Now, the form we'll come down to is this form. Now, notice the third equation is simply z equals 2. Now, because it's simply z equals 2, we can substitute back into the previous equation, the equation involving two variables. And if z is 2, you see, then 3 times 2 is 6, and we find y to be -1. And if y is -1 and z is 2, then we can substitute into this one and find the value of x rather easily. So this is just kind of a strategy of arranging our equations and eliminating certain parts of the system so that we can back substitute easily. Now, this arrangement is called row echelon form. And the method of eliminating these items to accomplish the row echelon form is called Gaussian elimination, in honor of the great German mathematician, Karl Gauss. Karl Gauss, by the way, is reputed to be one of the three greatest mathematicians who have ever lived. Anyway, let's see. Here's what we're going to do. We're going to think of this as a group of three equations. We're going to operate on these equations in this way. We know that we're allowed to multiply through an equation by some real number and have an equivalent equation. We know that we can add equations if we want to. So using those two techniques, we can actually change equations in such a way that terms are actually eliminated. We could also, if we ever wanted to, exchange a couple of equations in our arrangement of equations. Well, anyway, here's what we're doing. I'm going to copy the first equation. Whoops, that's a y. Okay, now here's what I want to do. I aim to eliminate the terms that are in these positions. That is, I want no terms in these positions. And I'm going to ask myself, gee, what do I need to do to these two equations to cause them to have an elimination of the term that goes in this position? Well, let's see, I see x and I see minus xg. If I just add the two equations, then I'll eliminate the item in that position. So all I'm going to do is add these two equations. Now, when you decide to perform an operation like that, put the information about your decision to the left of your bracket here. That is, here's what I want to do. I want to write, I'm going to take equation 2 and add it to equation 1. All right, so I'm just adding the two equations. Now, adding these two, I would get 0x, so I have a vacancy here. Adding these two, now I have to add all in all the other spots too, you see. Negative 2y plus 3y is simply y. And then 3z plus vacancy is 3z. And then 9 minus 4 is 5. All right, now I come back over here and I want to create a vacancy right here. Well, I'm going to play these two equations off of one another. That is, I'm going to perform some operation up here, and then I'm going to add these two equations. That's what I'm doing. All right, some operation up here. What operation? Well, I'm going to multiply that equation, equation 1, by negative 2. And then I'm going to add these two equations together to create the vacancy that I'm after. Now that's a lot of stuff to do. We have to both multiply in one equation and add with another one. So we have a lot of things to keep track of. Now we need to make a note about that operation. That is, we need to say to ourselves, I'm going to multiply negative 2 in equation 3, and then I'm going to add that to equation 1. You see, that's what I'm doing. Excuse me. I hope I don't confuse you here, but I made a mistake in that I'm multiplying negative 2 in equation 1. All right, it's negative 2 in equation 1, and then I'm adding equation 3. All right, I have to keep that straight, don't I? And I'm talking to you about high concentration. Okay, let's go. Negative 2 times equation 1, so that's negative 2 times x is negative 2x, plus 2x is no x, as expected. All the action, though, is in the other terms. All right, I can read back from my note here what I have to do in the other equations, or for the other parts of this calculation. Negative 2 times equation 1 and add equation 3. All right, let's do that. Negative 2 times negative 2y, that's 4y, minus 5y. Let's see, 4y minus 5y. Oh, that's negative y. And then negative 2 times equation 1, negative 2 times 3z is negative 6z, plus 5z is negative z. Negative 2 times equation 1 plus equation 3. Negative 2 times 9 is negative 18, plus 17 is negative 1. All right, now here I go. I need one more vacancy. I'm trying to create a vacancy right here. My first equation is in the form that I want it to be, so I'll simply bring it down. The second equation is just fine. I'm not going to operate on it at all, so I bring it down. Now, I want to think about what needs to be done with these two equations to create a vacancy here. Oh, the signs are different here, and so all I need to do is add those two equations. So I'm going to come out over here and make a note of that. I'm going to say, I'm going to take equation 2 and add equation 3. So I'm adding the two equations. All right, add these two, I get a vacancy here as expected. Add these two, 3z minus 1z is 2z. Add these two, 5 minus 1, I get 4. 2z equals 4. Now I'd like to create a situation where this is just z equals a number. What do I need to do? Well, all I need to do is divide by 2, you see, throughout this equation. So I'll come up over here, and I'll write my first two equations, and then I'll indicate what I'm doing to equation 3. I'm dividing by 2, and when I divide by 2, I find z to be equal to 2. Now, once I have the equations in this form, I go through this back substitution process. I know that if z is 2, then I can take this equation and replace z with 2 and find y to be negative 1. And now that I know z and y, I can find x by using the first equation. So the first equation, let y be negative 1 and z be 2, and we find that x is 1. Now we have a group of numbers that solves the system of equations. X is 1, y is negative 1, and z is 2. Now often the solutions in a system of equations like this is listed as an ordered triplet. X is 1, y is negative 1, z is 2. Now, if this is a solution to the system, it means that we can take these values and plug them into all three of the original equations and have truth. And we could verify that here. And that is a way for you to verify that if you ever question the answer that you get in a problem like this. One thing we can't do is put it on the graphing calculator, because the graphing calculator is limited to 2 axes, you see. All right, let's go through the process again, and this one contains a little bit of a nuance. Some troublesome things can happen in this environment, and I'm going to show you just a little hint of that here, but that's probably why we have other methods for solving systems like this, is because of the troublesome things that can occur. Well, let's go about the business of thinking through it the way that we did before. That is, we want to create this row echelon form. So we want to leave the first equation pretty much as it is, and we want to create vacancies under here and a vacancy in this position to create this row stair-step sort of effect. All right, now, let's see. We want to create a vacancy in this position. We're playing these two off of one another. Maybe if I put the bracket in here, it'll be easier to see. So this is equation 1, 2, and 3. So now we're working with these two. If we multiply in equation 1 by negative 1 and then add equation 2, we'll get the vacancy that we're looking for. So here's what we're doing. We're multiplying negative 1 in equation 1, and then we're adding equation 2. Now, by the way, in this pair, this instruction kind of thing, in writing this pair of values here or things here, here's the way you want to think about this. You want to write some operation on some equation other than the one that you're on, some equation above, and then you're adding the equation that you're in. That's generally the way that this is set up, and it's generally the way that it's easiest to think about. Because you might be thinking here, well, what if we take equation 1 and just add to the negative of equation 2? Well, it turns out that mentally it's a little easier to do your multiplying in equation 1 and then just add to equation 2. All right, so think about it like that. It'll help us with some stuff down the road as well. All right, so negative 2x plus 2x, 0x, vacancy as expected. The negative of 4y is negative 4y with negative 4y is negative 8y. Then the negative of z, negative z plus 6z is 5z. The negative of negative 4, that's 4, and 13 is 17. All right, now I'd like to create a vacancy right here. That is, I'm working with these two equations, and I want the item that is in this position to go out. So I need to operate on that rascal and add this. So I'm multiplying the equation 1 by negative 2. So it's negative 2 times equation 1, and I'm adding equation 3. You see, operation on another equation and then add the equation that you're in. All right, so here we go. Negative 2 times this is negative 4x plus 4x, 0x as expected. The vacancy occurs. All right, now all the action goes in this direction. Negative 2 times 4y is negative 8y, with negative 2y is negative 10y. Negative 2 times z is negative 2z, plus z is negative 1z. Negative 2 times the negative 4 is 8. 8 plus 6 is 14. Next step. I've got my first two equations in the way that I want them. That is, I've made this stair-step thing right here. The only thing I have left to do is cause a vacancy to occur here. But it's not quite so easy here. This is the nuance that I'm trying to show you here in this problem. Now, every now and then you get some mileage out of looking at coefficients and a constant, and you might have a chance to divide through by a common factor to eliminate it out of a problem. And I look for that here. I don't see it, but sometimes you can do that. Okay, we're trying to play these two off of one another. Whoa. Now, to do that, we're looking for the least common multiple for 8 and 10. Looks like 40. Wow, 40. Okay, so that's the least common multiple. Looks like we're going to have to multiply in both of them. Now, there's a lot to keep track of here, and we might need to use a calculator for that purpose. Maybe not for this first one, but maybe for the second or third one. But at any rate, let's see. I need to multiply here by 5 and here by 4, and I need to accomplish a sign change at the same time. So it's going to be, let's see, if I multiply here by 5 I'll make it negative 5. Negative 5 times equation 2 plus equation 3, excuse me, plus, wait a second, I have to multiply in equation 3. I can't just add it. So I have, let me give myself more room, negative 5 times equation 2 plus, now in order to get to that common multiple of 40, I need to multiply this rascal by 4. So it's plus 4 times equation 3. By the way, they're not going to get any more difficult than this. This is as hard as they get in this segment. All right, so when I perform all these tasks on these two rascals, I get 0 here as expected. All right, let's see. Negative 5 times equation 2. Negative 5 times 5 is negative 25. Then I want to add 4 times equation 3. So I got to keep track of this negative 25 and then minus 4z. So negative 25 minus 4, oh, that's negative 29. Z. And now, negative 5 times 17, calculator time, and then plus 4 times 14, you see, is what we want to add. With a calculator, we find out that that turns out to be negative 29. All right. Now, it's pretty easy to write this as z equals 1 when we divide on both sides by negative 29. All right, I've done that up here. I've just repeated the first two equations. And I have indicated that I'm taking equation 3 and dividing by negative 29 to give me z equals 1. Now the back substitution process is pretty easy. If we know that z is 1, then we can take this equation and replace z with 1 and solve for y. We find y to be 12 over negative 8 or negative 3/2. Now in this circumstance, when the problems get a little more challenging, a lot of times, rational values will occur, fractions will occur as the value of x, y, or z. So here we have y is negative 3 over 2. Now we know that z is 1 and y is negative 3 over 2. So we take equation 1, replace y with negative 3 over 2, replace z with 1, and away we go. We have a nice cancellation here, fortunately. The 2 divides 4, giving 2. 2 times negative 3, negative 6. And then collecting and adding 5 on both sides, we find 2x to be 1, so x is 1/2. And therefore, the ordered triplet, let's see, x is 1/2, y is negative 3/2, z is 1, so this ordered triplet solves the system of equations. After working with systems of 3 equations and 3 unknowns a little bit and going through the tasks that we have performed up to this time, you learn to notice some techniques that will gain some efficiency, that will give you some efficiency in the process. And one of them is this, that if you see 3 equations like this, and I'm looking at the leading coefficients here, it turns out that if the top equation has a leading coefficient of 1, a lot of times the arithmetic that follows will be made easier. So as a first order of business, I would just swap these 2 equations. So I'd put this equation as the top equation and then put this equation as the second one and then make some decisions from there. Well, let's see. Let's make some decisions from there. We would bring this equation down and then we would decide what we need to do to cause a 0 to occur in these 2 positions. Well, we would have to multiply in equation 1 and then add the equation in, add equation 2 and add equation 3. Well, to cause a 0 to occur here, we would multiply by negative 3 in equation 1 and then add equation 2. So that's what I'm indicating here. Negative 3 times equation 1 plus equation 2. When we do that, we get a vacancy here as expected. Then negative 3 times y is negative 3y with negative 2y is negative 5y. Negative 3 times negative 2 is 6 plus 4 is 10z. Negative 3 times 3 is negative 9. Negative plus 1 is negative 8. I'm almost getting confused here. All right, let's see. Then for this equation, for this position, we want a 0 here, so it's negative 2 times equation 1 plus equation 3, creating a vacancy right here. Let's go through the others. Negative 2 times y is negative 2y with negative 3y is negative 5y. Then negative 2 times negative 2 is 4z plus 6z is 10z. Then negative 2 times 3 is negative 6 with 8 is 2. All right, now our next order of business would be to cause this entry to become a 0. And by the way, it's valuable all along the way to look for opportunities where we can divide through by some coefficient or constant that is common to all of the terms. And sometimes even if it's not common to all of the terms, you get some efficiency out of it, even though fractions may be created. Like right here, I might decide to divide through here by -5 just to cause this term to become 1y. You see, the leading coefficient of 1. I'm not going to do it in this particular example because I want to show you something else about this particular problem. But sometimes you might gain some efficiency that way. Okay, let's take this step. I've just repeated this step up here because I want to make some decisions about this and show you one of the nuances involved in this kind of process. All right, we're trying to create a vacancy right here. We're playing these two off of one another. So all we have to do is multiply -1 times that and then add this. So it's -1 times equation 2 plus equation 3. The vacancy as expected occurs here. Now look at what happens to the other terms. We have -1 times equation 2. You see, that becomes -10z plus equation 3, that's plus 10z, that's 0z. So the z's went out as well as the y's. And then the real kicker is with the constants. -8, that's 8, and then plus 2, it gives 10. And then we notice that our variables have all disappeared from the left side, and our resulting equation is 0 equals 10, a false statement, and therefore there is no solution to this system of equations. You see, we're getting into the special cases where we have either multiple solutions or we have no solution at all. And this system has no solutions. All right, here's one that has many solutions. Notice I've already arranged the equation so that the top equation has a leading coefficient of 1. That'll help with our calculations a little bit. Now we'd like to create a situation in the next group of equations where we have a vacancy in these two positions. And we don't suspect that anything funny is going to happen at this point. All right, so what we'll do is we'll play these two off of one another. We're multiplying -4 in equation 1 and we're adding equation 2. So we'll write that down. It's -4 in equation 1 and we add equation 2. All right, this requires high concentration now. -4 times x is -4x plus 4x, 0x as expected. -4 times 2y is -8y minus 1y is -9y. Then -4 times equation 1. See, our notes are here and we refer back to it every time. So -4 times -1 is plus 4z, and 5z is 9z. And then -4 times 5 is -20, plus 11 is -9. Oh, and I'm noticing here we have 9, 9, 9. I can divide through by 9 and create some efficiency here, and I'll do that in the next step. All right, let's go to this one. We're playing these two off of one another to create a vacancy here. We'll need to multiply in equation 1 by -5 and then add equation 3. So it's -5 times equation 1 plus equation 3 is what we're doing, creating a vacancy here as expected. Then -5 times 2y is -10y, with -8y is -18y. Then -5 times -1, that's 5z, plus 13z, that's 18z. And then -5 times 5 is -25, plus 7 is -18. I'm noticing that I can divide through in equations 2 and 3 in order to create some nice things like leading coefficients of 1. In fact, many coefficients and constants of 1. Let's see what happens when I do that. I'm going to take equation 2 and divide by -9. And when I do that, divide this by -9, I get y. Divide here by -9, I get -1z. Divide this by -9, I get 1. Excuse me. My bad. Okay. And then in the next one, I'm dividing in the equation 3, I'm dividing by -18. Same kind of thing happens. Divide here by -18, divide here by -18, divide here by -18, and I get this. Now I'm noticing that these two equations are identical. Now let's see what happens if in the next step. I'm just using the same logic pattern that I used before. I'm going to bring down these two equations and decide what to do. And what I'm deciding to do is just multiply in equation 2 by -1 and add this equation. And when I do, and I'm just changing the signs of these rascals and adding those, and the sum will simply be 0 all the way across the board. So in indicating negative of equation 2 plus equation 3, I get 0 equals 0. Now here's where we have a true statement after a couple of variables have disappeared from the system. And now we have a system that has an infinite number of solutions. Now, your teacher may require that you only say that you have an infinite number of solutions and you can go on to the next problem. But it's probably the case that you'll need to have some way of generating that infinitude of solutions. And the way to do that is like this. You take this equation and solve it for one of the letters. Now, it's easy here to solve for y. So if I say that y is equal to z plus 1, then I'm solving for y. Now you let this letter used in the solution of y, you let that letter take on a value like a. Just name it a, some foreign letter. I'll tell you why in just a minute. All right, so if z is a, you see now we have a value for z. And then this becomes y equals a plus 1. So now we have a value for y. And since we have a value for z and for y, we can find the value of x by using the top equation. Here's the top equation. Y is a plus 1, z is a. We solve this, we find x to be minus a plus 3. So if x is this, then we have this ordered triplet, x, y, z. And a way to represent them, we have minus a plus 3 for the x, and y is a plus 1, and z is simply a. Now this allows us to generate values by letting a take on whatever value we select. For example, if a is equal to 0, then the ordered triplet becomes, let's see, 0 plus 3 is 3. 0 plus 1 is 1, 0. You see, if a is, let's say 2, then the ordered triplet becomes negative 2 plus 3 is 1. 2 plus 1, 3. This becomes 2. All right, so we can generate ordered triplets all day long. Now the idea of using a instead of like z kind of implies the third item in this ordered triplet. And we want to make our reference to any real number a that we choose, and not relate it to one of the elements in our ordered triplet. That's kind of the purpose of doing that. And by the way, we could have just let x take on the value a. We could have let y take on the value a. And here we let z take on the value a. But it'll work if a takes on the value of any of the other letters. We would just have a different kind of notation or a different kind of expression for the other items in the ordered triplet. But the set of solutions would be precisely the same, it turns out. Here's a problem that leads to a system of equations for solution. It says, write the equation of the parabola in this form. The equation will be in this form, which passes through these 3 points. Now, we're going to use a strategy that involves taking the information about the coordinates of these points and putting that information into the equation. Now, understand what we're doing here. We're given 3 points on a plane, and we're told that there is a parabola that contains those 3 points. And not only are we going to be able to draw the parabolic curve if we want to, but we're going to generate the equation describing that curve. Okay, here's what we do. We take the coordinates of these points, and we know that this relationship between equations and graphs is that the graph contains points, the points have coordinates associated with them, and the coordinates of those points will solve the equation. Well, with that basic idea, we're going to plug these xy pairs into this model. Now, when we plug in xy pairs, we're going to get as a result an equation involving a, b, and c. So we'll have 3 equations involving 3 unknowns. Well, let's see. We would begin here, if I choose to begin with this point, you see, then I would, in that model, I would write y equals, now I'll repeat the model here and then make the substitutions. Now x is 0, y is 5. So y is 5, x is 0. So here's what we're doing. Now these two terms go out, so we have found that c is equal to 5. Well, we do that for the other 2 points as well. Here we go. For the point 1, 6, you see, replace x with 1 and y with 6. So the y becomes 6, the x is 1. And we simplify a bit, we find 6 to be equal to a plus b plus c. For the point 2, 5, x is 2 and y is 5. So we have y is 5 and x is 2. Simplifying, we find this equation. Now we have the 3 equations. So we set this up as a system of equations like this, and we use the strategies that we've used before in this little earlier in this section. Now, so what we aim to do is create a vacancy in this position. So we're going to play these two equations off of one another. Now notice I've written the equation with leading coefficient 1 as the top equation here, just for the purpose of using this, this kind of technique. Okay, so we're going to multiply negative 4 in equation 1 and then add equation 2. So negative 4 times a is negative 4a plus 4a would be 0a as expected. Then negative 4 times b is negative 4b plus 2b is negative 2b. Then negative 4 times c is negative 4c plus 1c is negative 3c. Then negative 4 times 6 is negative 24 plus 5 is negative 19. And now I'll just bring down this equation. We don't have any work to do on it. Now we're ready to go through the back substitution routine. After all, we have c is equal to 5 here. So with that information, we'll jump right into this equation. So we take this equation and replace c with its value 5. Then we evaluate this for b. We find b to be 2. And then we back substitute a little further. Since we know that c is 5 and b is 2, we use our first equation, a plus b plus c equals 6. Replace b with 2 and c with 5, and we find a to be negative 1. Now what do we have? Well, we have the values for a, b, and c to plug into that general quadratic model. So we have the values for a, b, and c. Here's our general model. We replace a with negative 1, b with 2, c with 5, and here is the equation of the parabolic curve that goes through those 3 points. In this segment, we're going to examine a procedure in which we take an algebraic fraction and we rewrite it as the sum of 2 or more relatively simpler fractions. Well, the simpler fractions are called partial fractions, and the process is sometimes called partial fraction decomposition because we are decomposing the original fraction into the partial fractions. Here's how the process works. We start with a fraction that might look like this, and we begin by factoring in the denominator. Now, it turns out that the two partial fractions will have as denominators the separate factors that we have here. So one of them will have this factor and the other will have that factor as a denominator. Now the trick is to identify the numerators of these fractions. We'll identify those numerators as a and b. Now let's clear the fractions here by multiplying through by a common denominator. The common denominator would be the product of these two factors, and when we multiply these two factors in this term, we get simply 5 after the cancellation clears these factors. When we multiply x minus 3 times x plus 2 times this fraction, the x minus 3's cancel and we have a times x plus 2. When we multiply x minus 3 times x plus 2 times this fraction, the x plus 2's cancel, so we have b times x minus 3. Now, we still want to identify the values for a and b, and we do that by actually eliminating one of these terms or the other, and we can do that by letting x take on some very particular values. You see, what we've done here is we've set up a rather peculiar kind of equation called an identity. And you may recall that an identity is that kind of equation which is true for all real number replacements for x. Identities are often used in the description of properties, like the distributive property can be illustrated by using an identity. Well, we set up an identity right here, that this fraction is equal to that fraction for all x, for all values of x, you see. That's the idea. Okay, now, if that's true, then we can let x take on values that will cause each of these terms to disappear. For example, suppose we let x take on the value negative 2. You see, negative 2 plus 2, this term goes out. So now we have an equation involving only b, and x has already taken on this value, so we can solve for b fairly easily. So we have 5 then is equal to negative 2 minus 3, that's negative 5, so negative 5b. Dividing on both sides by negative 5, we find b to be negative 1. And now let's cause this term to disappear. We would let x take on the value 3. This term goes out, and we would have, well, let's see, 5 on the left, and then if x is 3, 3 plus 2 is 5, so this would be 5a on the right. Dividing by 5, we find a to be 1. So b is negative 1, a is 1, and we can write our fractions up above here as, let's see, the a value is 1, so we have 1 over the x minus 3, and then plus negative 1 for b over x plus 2. And because we have this negative 1 in this numerator, we would probably end up writing this as, so you just swap signs here, we would have minus 1 over x plus 2. Well, it's possible to check this partial fraction decomposition process, our answers in this, by using the graphing calculator. Let me show you the technique for doing that right quick. The first equation, y1, is the left side of our equation, the fraction on the left side of our equation that we saw a moment ago, and this is the right side of the equation. All we're going to do is verify that the two graphs of these two equations are identical. They just lay over one another. It might be helpful in doing that to deselect this first one. I'm pressing enter here and deselecting that equation for graphing. Here's the graph then of the first equation. So that left side fraction has a graph that looks like this. We want to just verify that the right side fraction has exactly the same graph, and therefore the equations would be equivalent. Well, I'm going to select now y2, and now both graphs will show up. Gee, we don't seem to see any difference. Well, that's good news, because it means that the two graphs are right on top of one another. To further verify the idea, we can press trace, and we can just jump from one graph to the other. Now notice the equation is written in the at the upper part of the screen with coordinates at the bottom part, but when I press either the up or down arrow button, I'll jump to the other equation, you see. And so we're just jumping from one graph to the other graph, one equation to the other equation, and therefore the left side expression has exactly the same value and is equal to the right side expression, and that's what we're verifying. In this example, the fraction to be decomposed is a little bit more complicated, but that's not a big deal. We follow the same procedure that we did before. It is important, though, to notice that the degree of the numerator is smaller than the degree of the denominator. Now, that is an important consideration. As long as that's the case, then we're okay following this procedure. All right, the process is to factor in this denominator. We snag out a common factor of x, and it would leave x squared minus 1. Then we factor that difference of two squares into these three factors. All right, so away we go. We set up our partial fractions according to the factors that we see here. We have one partial fraction for each of these factors. So we have this arrangement. Now notice that the numerators now are a, b, and c, and the trick is to identify those values. All right, we clear the fractions by multiplying through by a common denominator. The common denominator would be the product of all three of the factors here. When we multiply the common denominator times this fraction, the denominator factors will cancel, leaving the numerator. And over here, when we multiply these factors times that fraction, the x's go out, leaving these two binomial factors times a. So that's what we have here. Then these three factors times this fraction, the x plus 1's go out, and we have x times x minus 1 times b. And then these three factors times this fraction, the x minus 1's go out, so we have c times the other two factors. Now we want to choose, cleverly, values of x that will cause various terms to disappear. Now notice that in this arrangement of factors and the terms that a couple of terms share factors. That is, these two terms have x minus 1 factors in them. These two terms have x factors in them. And these two terms have x plus 1 factors in them. So if we want to find the value for a, then we look at shared factors by these two terms, and these two terms share the x factor. So if we let x take on the value 0, these terms will go out. Let's do that. Let's let x equal 0. All right, over here, these two terms will disappear, and we have negative 2 equals, let's see, on the right, those two terms are out of here. If x is 0 here and here, we have negative 1 times a, or simply negative a. And a then is 2. All right, that was easy enough. If we want to find the value of b, then we look at the factor shared in these two terms, and it's x plus 1. So we would let x take on a value that will cause that shared factor to become 0, and the value then would be negative 1. So let's let x be negative 1. On the left, negative 1 squared is 1, times 3 is 3. Negative 1 times negative 7, 7. 3 and 7, 10. 10 minus 2, 8 on the left. All right, let's see. This term disappeared because when x is negative 1, we have a 0 here. Term is gone. If x is negative 1, that term is also gone. If x is negative 1, we have minus 1, that's negative 2, times negative 1 gives 2, then 2 times b is 2b. Dividing on both sides by 2, we find b to be 4. To find the value for c, we look at the shared factor in these two terms, and it turns out to be x minus 1. The 0 for x minus 1 would be 1, so we let x equal 1, and these terms go out. Let's go over to the left. If x is 1, we have 3 here, negative 7. 3 minus 7 is negative 4. Negative 4 with negative 2 is negative 6, so negative 6. And then let's see, if x is 1, we have here 1 and 1, 2, times 1 is simply 2, 2c on the right. Dividing on both sides by 2, we find c to be negative 3. Now, let's rewrite our fractions. If the a value is 2, then we have 2 over x. We found b to be 4, so we have 4 over x plus 1. We found c to be negative 3, so we would have negative 3 over x minus 1. Instead of writing negative 3 up here, though, I'll make the minus sign the sign preceding the fraction, so we would have minus 3 over x minus 1. This problem contains an interesting nuance. It's the fact that we have two factors of x plus 1 in the denominator. Notice the denominator is already in factored form, so it's a little tough here maybe to see the degree of the polynomial denominator. Well, if we square this binomial, we'll get a quadratic factor. Quadratic factor times 2x would give a third degree polynomial. And a second degree polynomial in the numerator, well, we're okay to proceed as we have before. Now, we remember that our partial fractions take on as denominators all the different factors that we see in this factored form. The only trick here is that we have two factors of x plus 1. And it turns out that we need to have a partial fraction for one factor of x plus 1 and another partial fraction for two factors of x plus 1. So, in other words, the partial fractions will be a over 2x, then b over x plus 1 to the 1 power, and then a c over x plus 1 to the 2nd power. So we have to have a partial fraction for each of the different degrees of this multiple degreed factor. You see, if we had a 4th degree factor here, or a factor to the 4th power, 4 factors of x plus 1, we would have to have x plus 1 in the denominator of one partial fraction, x plus 1 squared in another, x plus 1 cubed in another, x plus 1 to the 4th in another. That's the idea. Okay, now we proceed as we normally would. That is, we want to clear those fractions, and we do that by multiplying through by this common denominator. Common denominator times this fraction leaves the numerator. Common denominator times this fraction, let's see, the two x's would cancel, leaving x plus 1 squared times a. So we have this. Then common denominator times this. One of the x plus 1 factors would cancel here, leaving the other one, you see. So we would have 2x times x plus 1 times b. And then common denominator times this term, the x plus 1 squares would cancel. Then we have c times 2x. All right, now we need to let x take on values that will cause some terms to disappear. The dilemma here has to do with finding a value for b, because look at what happens. B has with it factors that are consistent with both of the other two. If we were trying to find b and we said, okay, let's eliminate c by letting x take on 0, but if x takes on 0, then this goes out as well. We might say, well, let's eliminate a. If we let x take on the value -1, then we have -1 here, another 0. Well, here's how we handle that situation. All right, first of all, just choose a 0 of any of the factors. Now, I've chosen to find the value of a by looking at the shared factor in these two terms. That shared factor is the 2x. I'm letting x take on the value 0. When x is 0, then, on the left side, this goes out and we have -1. And over here, these two terms go out as expected. 0 plus 1 is 1, 1 squared is 1. So a is -1. All right, great. Now what about, let's see, what about our other factor? Well, we have, this can go out if x is -1. Now these two share a factor. So when I let x take on the value -1, I'm going to find the value of c. All right, let's just go through that and then we'll deal with b in just a second. All right, so we let x take on the value -1. And -1 squared is 1, so we have 4 minus 1, 3 on the left side. On the right, this goes out, and that goes out. And when x is -1 here, we have -1 times 2, that's -2 times c, -2c. Divide on both sides by -2 to find c to be -3/2. All right, now what about the value for b? What are we going to do? Well, notice that we've already found values for a and c. We know their value. You see, all we have to do is choose any value for x that we want to other than 0 and -1. Anything we want to, and just fill in the information that we already know concerning both x and the values for a and c, and then solve for b. For example, another value that's really easy for x would be simply 1. Well, if x is 1, then let's see, on the left side we would have 1 squared is 1, 4 minus 1 is 3. All right, that's fine. When x is 1 right here, we have 1 plus 1, 2. 2 squared is 4. 4 times a. Aha, a is -1. You see? So 4 times -1, that's -4 for that term. And then here for b, well, let's see, b is what we're looking for, but x is taking on the value 1, so 1 plus 1, 2. 2 times 1, 2. 2 times 2, 4. 4b. And then over here, if x is 1, we have 2 times c, but c has a value, and c's value was found to be -3/2. So we have -3/2 times 2, cancellation, -3. And now we have an equation involving b only as the variable. So solving it, we find b to be 2.5. And now we write our various fractions. We would probably set them up like this. Let's see, for a over 2x, if a is -1, we would probably write this as -1 over 2x. And then let's see, b is 2.5. We would probably think of that as 5/2. So we would write this as 5/2 over x plus 1. And then the c value is -3/2. So instead of putting plus here, I'll put minus, and then 3/2 over the x plus 1 squared.